Students, today we will learn about the VBT diagram of coordination number 4. Example is NiCN4 2 negative. Electronic configuration of Ni2 plus will be 3D8. Cn is strong field ligand that will cause the pairing, result in the dsp2 hybridization that will accommodate lone pair of Cn. The geometry will be square planar and the nature will be diamagnetic as there is no unpaired electron present in the electronic configuration. Let's start with our first example, tetracarbonyl nickel. The oxidation state is 0. Electronic configuration is 3D8 4s2. Carbonyl is a strong field ligand, result in the pairing of electron from 4s to 3d orbital. Now the 4s and 4p3 orbitals get hybridized to form 4sp3 orbitals. Lone pair of carbonyl will get accommodated. Molecule is diamagnetic and the symmetry is tetrahedral. Another example is tetrachloronickel 2 negative. The electronic configuration of nickel atom is 3D8 4s2, nickel 2 plus is 3D8, Cl is weak field ligand, so no pairing, 1 4s orbital and 3 4p orbital hybridized to form 4 sp3 hybridized orbital that will accommodate the lone pair of Cl ligand. sp3 hybridization make the molecule tetrahedral. Presence of unpaired electron make the molecule paramagnetic in nature. You can see there is two unpaired electrons, so the molecule will be paramagnetic in nature. Now, dimethyl dioxime nickel. As we know that DMG is a strong field ligand, this will result in the pairing of electron, making the 3d5 orbital vacant. Result in the dsp2 hybridization. Symmetry of the molecule will be square planar, and as we can see there is no unpaired electron, so the molecule or the complex will be diamagnetic in nature. Another example is of CuCl4 2 negative. In this complex, one electron from 3d5 orbital will jump to 4p3 orbital to make the 3d5 orbital vacant, which results in the 3d5 sp2 hybridization. One unpaired electron makes the complex paramagnetic, although the structure of the complex is flattened tetrahedron structure, not the square planar. That could not be explained by this VBT. Another same type of example is tetraamine copper 2 plus. Copper 2 plus have 9 electron in its 3d orbital. As ammonia is a strong field ligand, this will cause flipping of 3d5 electron to 4p3 orbital. Now, 1d5 orbital, 1 4s orbital and 2p3 orbital combine to form 4dsp2 orbital, hybridized orbital that will accommodate the 4 lone pair electron of amine. The structure is square planar and the molecule is paramagnetic due to the presence of one unpaired electron in 4p3 orbital. But if it is so, then copper 2 plus can easily be oxidized to copper 3 plus by losing its outermost electron. Huggins have given a suggestion for this complex. As per Huggins' suggestion, there is no flipping of 3d5 electron from 3d5 orbital to 4p3 orbital, and the hybridization will be not dsp2 type, but it will be sp2d type. You can see in the picture that this electron will not move from here to here, and hybridization will be occur in between this s, this 2p orbital and the last d orbital. So this can be the example why the copper will not get easily oxidized, because the electron is present in the inner orbital of the central metal atom. Another example is of tetracyanoplatinate. The electronic configuration of Pt2 plus is 5D8. Cn is a strong field ligand, so this will result in the pairing of electron from 5d5 orbital to 5d4 orbital. The hybridization occur for this central metal atom will be 5d5, 6s2 and 2 6p3 orbitals, result in the 4 orbitals of same energy that will easily accommodate the lone pair of electron of Cn. The molecule will be square planar and diamagnetic in nature. Another example of the same is given on the slide, you can see here. Now, some limitations of VBT. It doesn't explain the magnetic properties and data of coordination compounds, can't explain the color of the coordination compounds, doesn't explain the thermodynamic or kinetic stabilities, unable to differentiate between weak and strong field ligand. Its prediction about the tetrahedral and square planet structure of 4D coordination compounds are not up to the mark. It predicts no distortion in symmetry compounds. It does not explain why at some times Hund rules will be followed and sometimes not. It gives only qualitative explanation for the complexes, not the quantitative explanation about